Continuing, we can introduce the concept of conductance. Conductance, denoted by the variable G, has units of Siemens, which is 1 per ohm. Now, from Ohm's law, we can express the current running through a particular element, I is equal to V per R, or in units of conductance, it would be G times our voltage potential. That is, we can say I1, our current running through resistor 1, would be equal to the conductance of that element times the voltage potential across. For R2, our current running through our system, I2, would be equal to the conductance of that particular element times the voltage potential across. Now this has an interesting consequence. If we apply KCL in Ohm's law at node A, we can solve for our current running through R1 and R2 in terms of our source current as well as the conductance of each element. Applying KCL at A, we have our source current entering our system is equal to I1 plus I2. If we express I1 and I2 in terms of our conductance and voltage potential using Ohm's law, we can say our source current is equal to G1 plus G2, that quantity times our voltage potential, where we define our equivalent conductance, GEQ, as the sum of G1 plus G2. If we solve for a voltage potential across our resistors, we can say our voltage potential V is equal to our source current per our equivalent conductance. Now, if we want to determine I1 and I2, i.e. solving for the current through each leg of our system, we can do such by applying Ohm's law. That is, our current running through I1 would be equal to our conductance, G1, times our voltage, where our voltage was equal to our source current per our equivalent conductance. That is, I1 would be equal to the quantity, G1 per G1 plus G2 times our source current. Now we can verify this is equivalent to our previous expression if we express our conductance now in terms of resistance, where we would get the same expression as before. A very interesting consequence of using conductance is when we're solving for I1, we're running through R1, we express this in terms of our conductance within our numerator per the sum of our conductances within our parallel configuration. This differs from if we express this in terms of resistance, where we'd have our opposing resistance R2 within our numerator per the sum of our resistances in our parallel configuration. Now, if we applied the same methodology, we can solve for I2, which is our conductance G2 per our equivalent conductance G1 plus G2 times our source current. And if we compare this to our previous result using resistances, we see the difference of having our conductance within our numerator for our element of interest as opposed to our opposing resistance of a resistor in our parallel configuration. Now, to formalize this, we can look at a general case where we have a current source that is feeding current to various resistors with conductance G1, G2, G3, all the way up to Gn. Now, if we apply KCL at node A on our left-hand side, we would have the following expression. Our source current would be equal to I1 plus I2 plus all the way up to I sub n, where capital N represents the number of resistors we have in our parallel configuration. If we apply Ohm's law to our KCL equation, in terms of conductance, we can say our source current is equal to G1V plus G2V all the way up to G sub n V. Now we recognize we have the same voltage potential across each of our resistors within our configuration. Thus we can say our source current is equal to the sum from I is equal to 1 to n of G sub I times V, where we define G sub I summed from I is equal to 1 to n as our equivalent conductance within our system. Lastly, if we are interested in finding the current flowing through any particular resistor of interest, we can express this as I sub n would be equal to the conductance of that particular element of interest per our equivalent conductance times our source current, where equivalent conductance is the algebraic summation of the conductances of our resistors in our parallel configuration.